The first of the Coulomb-Mohr theories is the ductile version of it, the ductile Coulomb-Mohr theory, DCMT for short. It's again a shear stress based failure criteria, and this is to be used for only those ductile materials that do not have the same yield strength in tension as they have in compression. So their compressive yield strength is different than their tension based yield. So that's not the case with steels. Steels have the same, almost the same S of Y in tension as they have in compression, but in some softer metals that's not the case. Most grades of aluminum have a yield in compression that's a lot more KSI, a lot more MPa than they have in tension. So it's only to be used for those materials, those ductile materials only, whose yield strengths differ in compression and tension. And the theory states that failure begins when the Mohr circle of the state of stress at a critical point exceeds the envelope created by the two Mohr circles, for one for uniaxial tension test and the other Mohr circle from a uniaxial compression test at yield point. So it's kind of the harder statement to make sense of. But what it's saying is, if you take a little piece of aluminum, let's say this is only for aluminum kind of materials, take a little piece of aluminum, put it under a tensile test, take it to yield point, and then plot the Mohr circle of a point, and that Mohr circle will be, let's say, let me maybe try and mark it here on this Mohr circle that you see is the Mohr circle. The one at the extreme right is the Mohr circle at yield point in a simple uniaxial tension test in a component on a component done in the lab. Do the exact same test, but do it on a compression test bed, and what you would get is another Mohr circle at yield point, and that is this Mohr circle right here. Don't know if you can see the yellow on the board. I'm pretty sure you can. So there are two Mohr circles, one for the two cases done in the lab. And so what you want is then look at the envelope created by that, and the envelope created by the two Mohr circles is this. Maybe a little bit down. The first one should be a little bit down, and that is the line that you see. Still up there. Yeah, for some reason I can't get it down, but that line A to E that you see is really that line, so I'm not even going to try. Maybe you can try using this command here. That's still up there. Yep, that line. So this is the lower bound to that envelope created between the two Mohr circles, and that's the upper bound. So you look at this space, and then what you do is you look at the state of stress, plot the Mohr circle of the actual component at a point. And then if that Mohr circle is completely enclosed within this space and this little area created by these two Mohr circles, then you're safe, and if not, you're unsafe. So and what that really means is, if you look at failure, then failure happens when sigma 1 divided by this. When this is true, sigma 1 divided by S of yt, yield strength and tension, minus sigma 3 divided by S of yc is more than 1. That's when failure occurs. So if you have if you look at the safety condition, then therefore it is sigma 1 divided by S of yt minus sigma 3 divided by S of yc is less than 1 divided by n. This, however, the figure that you see on the right of the screen, the three Mohr circles plotted, that's not the safety envelope the way we have been looking at it for DET, MMST, and SST. The safety envelope we sketch is actually on the sigma A, sigma B axis. So there is one for this one as well. And it looks exactly like the MSST safety envelope, except that now that you're not dealing with a single value of S of y, you actually have one S of yt and another S of yc. That's what your extremities of the safety zone are. So if you look at on the right and the top, these are SYT divided by N. Just like for MMST, it was just SY divided by N. And on the left and the bottom is actually on these two coordinates on the plot, they are negative SYC divided by N. So yield strength and compression here and there, and yield strength and tension is these two. Okay, and then you can look at the three cases, but case 1 is there, case 2 is there, and case 3 is right there. So that is about DCMT. It's just, it's actually a general form of the maximum shear stress theory. So the way to look at it as a general form of the maximum shear stress theory would be to, let's see, let's write DCMT, the form for DCMT, and that is sigma 1 divided by S of YT, yield strength and tension, minus sigma 3 divided by the yield strength in compression is less than equal to 1 divided by N. That is your safety condition according to the ductile Coulomb theory. If the two yield strengths are the same, if S of YT is equal to S of YC, which happens in most steel type of materials, and they're both equal to something called S of Y, that's what we call it. If they're the same strengths, S of YT equals S of YC, then we'll just call it S of Y. In that case, then what happens is now I can replace both these by just S of Y's and rewrite this as sigma 1 minus sigma 3, exactly this. I can take this S of Y up there, and it will be S of Y divided by N. And what was this? This is the safety condition for the maximum shear stress theory. So you can consider maximum shear stress theory to be a special, a very particular case of the ductile Coulomb theory. It's MMST is a special case of DCMT when the yield strengths, when this is true, when the yield strengths and compression and tension are the same. Okay. And let's look at the brittle version of this theory. It's exactly the same. It's the brittle extension of the ductile Coulomb theory. It's useful for ceramics and cast brittle materials such as iron. So cast iron, it works very well, the brittle Coulomb theory. And it says the statement is exactly like the ductile Coulomb theory. All you do is you're not talking about S of Y. Now you're talking about S of U. You consider S of U now. So you replace S of YT by S of UT and replace S of YC by S of UC, ultimate strengths now, instead of the yield strengths, and you will get you'll get the safety condition. You'll get the brittle Coulomb-Mohr theory safety condition. This looks exactly like the ductile Coulomb-Mohr, except that S of Y is replaced by S of U. So, and the safety zone looks the same, except that these are S of UT instead of S of YT divided by N on the top and the right, and the left and the bottom coordinates are negative S of UC divided by N, not S of YC. So again, to recap this, it is DCMT is only for ductile materials, and it is sigma 1 divided by S of ultimate strength and tension minus sigma 3, the minimum principal stress, divided by ultimate strength and compression should be less than 1 divided by N. And your brittle Coulomb theory, BCMT, is nothing but sigma 1 divided by S of UT. For brittle materials, there's no yield strength, and sigma 3 divided by S of UC is less So kind of the same basic equation, just the strengths are not the same. They're different values. Okay, so we'll stop here, and the next video file for this will be the one dealing with modified Mohr theory. There's another thing called modified Mohr theory. That'll be the last one we do.